Hi everyone, thanks for tuning in to see this first video in the short series, and in these videos we're going to be taking a look at points, lines and planes. We're going to be having a good delve into the geometry associated with points, lines and planes, and maybe some of the typical questions that might come up. But before we go to worksheets and start working through questions, I'd like to use SolidWorks here to explore various types of planes and in various ways of working with planes and questions and problems that might crop up that we need to be able to solve. Everything on this video is going to be based on these two planes here, my yellow and blue planes. And if I've just drawn these before the video started there, made them much longer than you'd usually be used to seeing. So I'm going to have, I think it's 7 models at different positions across these planes. If I just zoom in here for the very beginning of this, I'm going to be starting over here at this side. It's just my vertical and horizontal plane, so the usual ones that we're used to seeing. The vertical plane and the horizontal plane intersect along a line of intersection that we always called the XY line. Any other plane that's put in, and a plane is simply a flat surface, it's of an unlimited size. Any other plane that we put in, as long as it comes in contact with any one of those two planes, it leaves what's called a trace. So when we start exploring different types of planes, we're going to be talking about the traces of the plane. Now I'm going to go ahead and we'll start off very basic, we'll work up to more difficult ones. The very first plane I'm going to put in there is a horizontal plane. So it's parallel to the ground. It's at a set distance from the ground, and it is perfectly horizontal. Now a plane is a perfectly flat surface. Now I've given this a limit because I wanted to fit on screen, but a plane is an unlimited size. This plane right here only has one trace, and a trace is a line of intersection that our plane makes with the two principal planes, that being our vertical and horizontal. So this plane right here, this horizontal plane that's after being dropped in here on SolidWorks, has one trace, and that is the trace right along. It won't really let me select it now. The trace is right along here. That is called a vertical trace. A trace is a line of intersection, and that line of intersection is where it intersects the vertical plane, so it's a vertical trace. So that line along right there is the vertical trace of this plane. This plane has no horizontal trace because it does not intersect the plane. Okay, so if we manipulated this plane and changed it around in such a way that it touches both the vertical and horizontal, well then it would have to have a vertical and a horizontal trace. So right now that is just a horizontal plane. The simplest version of one trace only. A vertical plane is next, and the vertical plane is right there. So it's a plane that just stands straight up off the ground. It's a very easy plane to imagine and to visualize what's happening. It has two traces. It has a vertical trace standing straight up along the vertical here. It has a horizontal trace coming out along. It's perpendicular to both planes in this case here. So that's just a simple vertical plane. They wouldn't be two very common planes that would come up as part of, let's say, a leave insert long question or anything. They're just a bit too simple. Maybe we'd use them, and we have plenty uses for them, but really we need to be getting into something with a little bit more difficulty and a little bit more visualization involved if we want to be testing ourselves. So we'll just move on to one more here, which is just called a simply inclined plane. And what the term simply inclined means, unlike the previous two, which were just very basic, this one here stood at 90 degrees to the vertical, parallel to the horizontal. This one here is perpendicular to both planes. Well, this one here just makes an angle with one of the planes here. It makes an angle of, let's say that, what's that angle? That might be about 70 degrees. It makes it roughly a 70-degree angle there with the vertical, and it's just standing straight up perpendicular to the horizontal. We call that a simply inclined plane. It is simply inclined to the vertical. So it makes approximately a 70-degree angle there to the vertical plane. What we might be asked to do sometimes is to find the true shape of the planes, or we might be asked to rabat the planes. So I've, in the 7 or 8 examples I have here, I've kind of gone through everything we could be asked really. What in this case, I can't remember what we did here. I did here first, it was a rabatment about, okay, it was to rabat and find the true shape of that plane. Rabat it about the horizontal trace. So as I said there at the start, this plane here touches both the vertical and horizontal. Where it touches gives us a trace. So there's a trace standing up along here, and there's a trace coming out along here. So in this one, I'm setting up a scenario where we've been asked to rabat and find the true shape of this plane by rabatting it about the horizontal trace. So use that horizontal trace down there on the ground as a hinged line and swing it out from there. So using this corner point right here is the point our compass would go on, and we swing it out and drop it down onto the ground, and we do the same then from this front point just here, and when it goes down the ground then we'd be able to see a true shape of it. So there's just one little scenario there where we can rabat a plane about its trace and drop it down onto the ground or down onto the horizontal plane. So that's just one scenario. Now moving on ahead again, I have another simply inclined plane here. It is simply inclined to the vertical. This time it's probably making an angle of about 45 to 50 degrees or something like that. It stands straight up, perpendicular to the floor. And the second scenario I'm after coming with now, this time I rabated it about the horizontal trace, and the trace being the line of intersection that it makes with the horizontal plane is the horizontal trace. This time I'm going to rabat it about the vertical trace up here, and you can see that happening. I've taken a point in the vertical trace, I have rotated around. I'll do the same now for the top point here. Rotate it around onto the vertical plane, and there it is. That's the true shape. So that's a very simple one really to imagine, because you know it's like the hinge on a door, and you're taking that door, swinging it around, and as I look in straight in, and this is going to go really big and I'll have to zoom in again. As I look straight in, it looks so small here, and then it gets swung all the way around and back, and it's directly in front of me on the vertical. So as I'm looking at an elevation of this object, I see a true shape. If I look down on the plan of the object, now the edge view, it's only a surface I've used here, so the edge is almost missing, but there's the edge view, swung all the way around, touching a line parallel to the XY line or parallel to the vertical plane, and then we look in at our elevation and we see our true shape of the plane right there, that simply inclined plane. So there's 2 rabatments right there. Simply inclined to the vertical plane. Both of these, the grey one and the red, are simply inclined to the vertical plane. That is rabatting it about its horizontal trace, and this one here rabatting about a vertical trace. So there's our first 4 little models to show the basics. Moving on to number 5. This one here is simply inclined to the horizontal. So it stands directly at 90 degrees from the vertical, but it makes an angle of maybe about 60, no, a bit less, maybe about 55 degrees there. Probably makes about a 55 degree angle there with the ground, with the horizontal. So this plane would be defined as simply inclined to the horizontal. And again, just like before, we might be asked to, because this is all we can see. When we look in from the front, we see, well, we can't really even see it there. There it is. When we look in from the front, it's an edge view. When we look down from the top, it appears as a rectangle, but it's not a true shape. It's not at all, nowhere near a true shape. It appears much smaller than it is in reality. So we might be asked this again. We have a vertical trace up along here, the line of intersection with the vertical plane. We have a horizontal trace coming out here. We might be asked to rabat this plane about the vertical trace or about the horizontal trace, and we need to be able to do that. So right now, this time, what have I started off with? I'm after rabatting it there about the horizontal trace. So as I look in at the elevation, I can take my compass on the point view of the horizontal trace, and I can swing it until it hits the ground. So there's a rebatment about the horizontal trace. I have to do the same with the second point, and I get the true shape of the plane laid down the ground right there. Okay, so that's as seen in elevation. We can draw our arcs because we have a point view of the hinge line of the horizontal trace, and we can swing it out, drop it on the ground, and when we look down on plan, we see our true shape. So simply inclined to the horizontal plane right there. The next scenario, again, simply inclined to the horizontal plane, just like this one right here, making an angle of approximately 60 degrees there to the horizontal plane. I have my vertical trace up along where it intersects the vertical plane. I have my horizontal trace coming out along here. And this time, well, the last time I rebatted about the horizontal trace, this time I'm going to rebat it about this vertical trace. Now on paper, this, like, it just doesn't really make sense for a while on paper. Maybe once you've seen it here and seen the real model, you see how simple it is. It's so easy to overcomplicate something like this. Rebatting about the vertical trace means, like, really we'd have to be looking right down along and get a point view of the vertical trace there. And then we can see our compass arc. Now if I bring in the next one as well from the top point there, it just overlaps perfectly. And that is a rebatment about the vertical trace. So there's the vertical trace. If that's the hinging line, I should be able to see the hinging line as a point, and then I should be able to take my compass and swing everything, and it results in a true shape as seen in elevation. So that's a rebatment about the vertical trace. Now what we'll need to be looking at when we go at this one on the worksheets is, that's what it looks like. There's the edge view right there. As always, the compass strike is appearing as a line that is perpendicular to the hinge. So the rebatment always happens perpendicular to the hinge. The movement of the points is perpendicular to the hinge. So we'll keep that one in mind when we get onto this on a worksheet. That's it for horizontal, vertical planes. Simply inclined to the vertical, simply inclined to the vertical again, with the two different types of rebatment happening there, rebatting about the horizontal, rebatting about the vertical. And over here then we had simply inclined to the ground, to the horizontal, with a rebatment around the horizontal trace, and we had a simply inclined to the horizontal with a rebatment on the vertical trace. That's going to be it for now. We're going to go ahead and get onto our worksheets and see how the principles and how the theory we've just seen here on SolidWorks, we'll see how that feeds back in to solving some basic problems on our worksheets. So let's take what we've just seen in SolidWorks and bring it on here to solving some problems on our worksheets is the next step here. Worksheet number 1 here says draw a simply inclined plane inclined at 60 degrees to the horizontal. So just very simply, the horizontal plane is seen as an edge view in elevation. The plane that is inclined, the simply inclined plane that's inclined at 60 degrees, well, anywhere at all along the line, there's our 60 degree vertical trace. There's the VT. So we can see an edge view of the plane up there. It is simply inclined at 60 degrees to the horizontal, but don't forget the horizontal trace, which just stands straight out. And if you're not sure of any of this, you need to just flick back in the video a little bit and see what the simply inclined to the horizontal plane looks like. So there's my H. There's my vertical trace. It stands at an angle there of 60 degrees. Next one is draw a simply inclined plane which is inclined at 75 degrees to the vertical. So this time we're talking about the vertical, so we're looking down on plan. The XY line is the edge view of the vertical, and I want 75 degrees. I could use my 45 and 30. I'm just going to use this here. Rise that up there to 75. Simply inclined at 75 degrees to the vertical. Anywhere at all, again, it doesn't really matter for these questions. There is my horizontal trace. That horizontal trace represents an edge view of the plane. That plane makes 75-degree angle to the vertical plane. And then of course we need a trace up top as well, and that's just a line standing straight up. There's my horizontal trace. So there's the first two basics. As I said, if you're not sure why I did anything to here, you need to be flicking back along the video back to an earlier stage and comparing this to what you saw on SolidWorks. Moving on ahead, on to number 2 here. Number 2 is saying rabat the simply inclined plane about the vertical trace. So we saw this as our third, was it? No, we saw this as our 5th. 1, 2, 3, 4. I'm just looking at my SolidWorks screen again. 6th actually. The yellow little object on SolidWorks, we saw this one right here. Rabat the simply inclined plane about the vertical trace. Now, not a very nicely set up question. First thing I'm going to do actually is I'm going to just shorten this vertical trace down to here. So there's the VT and there's the HT up there. As I said a while ago, I'm not going to go over complicating this at all and using auxiliaries or anything like that, but we do know that the movement of all points on the plane is perpendicular to the hinge line. So we're going to rabat it about the vertical trace right now. I'm going to take the angle of the vertical trace and I'm going to go perpendicular. Now I'm after shortening the plane because I just wanted it all to fit here nicely on the page. It moved a little bit. And if I want to ensure that whatever portion of the plane is shown here in plan, well, the trace is on the plane is that long. That's what's shown in plan, and I can make my one here the very same length. Now I could have done that by swinging up as well, but that's it really. You know, it's the sort of question that could easily be overcomplicated here, and there's no need. We just have to remember the little rule that the movement of any points as they rabatted is perpendicular to the hinge line. So not the best setup of a question, because if we had gone with the top of the vertical trace there, the plane would be much bigger, would go off the sheet. But that is it. There's a perpendicular movement there from the 2 points that I chose in the plane, one being on the horizontal trace, and then I just stopped at a random point up along and moved them. And I'm going to work with the length of plane they gave me here, but realistically anywhere I stop is still a portion of the same plane. So rabatment of a simply inclined plane right there. This one, sheet 3 here, that was sheet 2 that's finished now. Sheet 3 here is a little bit more practical. I think it's more of a question that we can actually visualize and kind of get into. Once again, I'll just for habit, there's the vertical trace and the horizontal trace. Rabat the simply inclined plane about its horizontal trace. This is, if you want to look back in the video, it is model 1, 2, 3, model number 5 there, the blue one, and we can see an edge view of the plane in here. The horizontal trace, when we look up along, appears as a point right here. So the rabatment is actually very easy. We just take our compass from T, bring it up to the point V, rabat it down onto the ground. There it is on the ground. If it's on the ground or on the horizontal plane, it's a true shape in plan. So there's my rabatment right there, and that is my true shape. It's my rabatted plane right there on the ground. That's sheet number 3 done. I'm working through these nice and quickly, and what I'll assume is that anyone that's watching the video, if you're stuck, you might have a look back at SolidWorks and see where all these are coming from. There's no point in just copying an arc and 2 lines. Understand where it all comes from by looking back on SolidWorks and by seeing it there. Now, before I go on to sheet number 4 here, finding the elevation of points, and then also on sheet number 4, there's my VT and there's my H. My vertical trace and horizontal trace are very different looking. I'm going to go back onto SolidWorks again. I'm going to go through a model, and this would take me all the way from sheet 4 up to, I think it's sheet number 13 on this set of handouts. So back to SolidWorks now for a few minutes. Now, having looked through the 6 models that were here, we've now got a chance to practice, and I think we've practiced these two here. These two weren't actually asked on the question sheet at all. Sketch them, go through it, make up your own question sheet, but make sure you understand them anyway. We've just gone through this one here as the last one. So as we see the elevation, and we're bashing it down onto the ground and seeing it as a true shape down in plan, and the one before that was this one here. We're bashing our simply inclined plane, and just all we can see is the perpendicular movements, no need for anything else. Getting on to something there in sheet 4 though, where we're given traces that don't quite look as easy as those ones. So we're basically moving on to the real meat of the topic here. That's oblique plane. Now there so no, bring this on one more step or 2 steps maybe, and there we have it. An oblique plane is a plane that makes a certain angle with the horizontal and with the vertical. So the traces usually end up pointing in towards each other, either towards the left or maybe towards the right. But that is an oblique plane. What's really important with oblique planes is this. As I look in at the elevation, that line right there, which is the vertical trace, that trace makes an angle of, let's just say, I think that probably looks around 40 degrees. That trace makes an angle of, we'll just say 40 degrees right there. But that is not the angle that the plane makes with the ground or with the horizontal, because the angle that the plane makes can only be seen all the way over here. Now, in a view something like this, I can see that the angle that the plane makes is actually much, much higher. That's up on about 50 or 52 degrees right there. So the angle that the trace appears to make and the angle that the plane actually makes are two completely different things. The exact same as if we look down on top of this here and see the plan. As I see the plan of this guy right here, I see that appears at approximately 32, 33 degrees right there. But if I want to see the true angle that oblique plane makes with the vertical, I'd need to move on over here and see the true angle right there. Now move it slightly so we can actually see that is the true angle right there. And again, these angles are changing. They're completely different. The angle that the trace makes and the true angle of the plane are two completely different things. Now we will get on to that maybe in the next video, but it's just something to be aware of. These oblique planes are just a plane that makes a specific angle with the vertical and horizontal. And there's quite a number of questions that can be associated with them. Here's the first. Movements of a point and projections of a point. So as we look at this oblique plane, I have dropped a point here, point P on the plane. Point P is directly below, obviously in plan, as you're looking at the plan view of the object, it's directly under point P, and in elevation it's going to be directly in front, so here someplace there. And to link them up there, just to show what it looks like as you project down on the plan and in the elevation, well, that's all we're doing. We're just taking the point and projecting it onto the plane, and in plan take the point and project it down onto the plane. What we need to do next though is on paper we need to be able to find all these points. This is 3D space. In 3D space, in SolidWorks, I can open up sketches and 3D sketches, and I can make sure that these lines are vertical and horizontal and so on. It can all be done in 3D space, but it's actually drawing it on paper is the next thing. And what we need to do for the transfer of points and manipulating points from one view to the next, we need to be able to section the object, or what that means is cut the object. We need to be able to see what it and imagine what it looks like when we cut the object. Now the first cut I'd like to show is parallel to the top plane, which is a horizontal cut. Now horizontal cut, as you can see, I'm cutting everything. I'm revealing a cut line along my oblique plane, I'm revealing a cut line along my vertical plane. So if we just have a look now, I'll bring my horizontal cut plane down until I'm hitting point P. So right down there until I'm hitting point P, which is there. I'll just accept that for a moment. So a horizontal section through point P, what does it give us? The first thing is first, if we're looking at the elevation of this, zoom back into my question, horizontal section through point P. As I see an elevation, well, it's horizontal, it's a horizontal section, so it's a horizontal line across there. The more interesting one is when I look down on my plan, the horizontal section that I just cut through point P gives me this line along here. That line is parallel to the horizontal trace. That's a little bit of theory we need to know. Any horizontal section through a plane is going to give you a cut line that is parallel to the trace. We can see from my 3D sketch from earlier the way that the points line up perfectly, but we can also see now that if we go from the point parallel to the trace up and hit the vertical plane right there, hit the XY line, which is the vertical plane, there's going to be a relationship here where we come from our plan up to our elevation, touching the trace, and straight across. So if I just show you what that looks like now, my horizontal section, as I have it sketched in, is there. And there it is, in blue, if it's possible to see it there. From the point in plan, we go parallel to the trace. That is this line right here. That is a 2D representation of this cut right here. That point is the plan of that point. So in plan, parallel to the trace, up to hit the vertical trace, and across will give me my point. So if I just zoom out a little bit, turn off my plane, my section plane, that's what you get. When I cut that horizontally through the point, we can see it in 3D the way I get my cut surface right there, and that cut line is parallel to the trace, but we cannot see it in 2D really here. We see that on paper. And when we go to solve this question on paper, if we're given that point in plan, I'm going to go parallel to the trace until I hit my XY line. I'm going to come up until I come onto my vertical trace, and I'll come across horizontally until I hit my point P. So that's going to be the theory. That's the background to the theory that we're going to use on paper. Let's turn that off. The next one then is I'm going to hide that horizontal section, and I'm going to turn on my section plane again, but this time I'm going to go with a vertical section. I'm going to bring out a vertical section plane until I'm touching the correct point. Let's see, there it is. I think that's probably close enough. And what does that get me? That vertical section, and it's after hiding all of the detail there. Okay, the colors are gone, but that's okay. That vertical section plane, when I look at it in plan, it's a line that's parallel to the vertical plane. So it's parallel there to the XY line in plan. It's a vertical section. In elevation, though, is the more important one. In elevation, it gives me a vertical section through a plane, gives me a line parallel to the vertical trace. So if I cut this plane anywhere along, if I just move it back to show this a little bit more clearly, anywhere that I cut this plane along gives me a line parallel to that trace. So it keeps moving out, but the line is always, that section line right there is always parallel to this trace. Let's see what that looks like on what it would look like on paper. That is the detail of a vertical section right there. So there's my vertical section through the point. It gives me a line parallel to the trace. That's my green line here, parallel to the trace, onto the ground. We bring that point down to hit the horizontal trace and across to catch point P. So there's two representations in green, one in green for a vertical section cut, and if I just turn the other one back on for a minute, one in blue for a horizontal section cut. Either way, if we're given these traces and we have a point in one view, we can go ahead and find that point in the second view using any one of our two methods. Similarly, if we have the point P in elevation, we have the point P in plan, and if we have only one trace, we can go ahead and go parallel in plan, up, and we can go across and we can find the trace. So there's just quite a bit going on there, a lot to understand, a lot to visualize, but the great news is a lot of problems you'll be able to solve using that. So let's get back to paper, let's solve a few questions using this. And the only other little thing to remember here is, if you can take 1 point, you can take 2 points, and 2 points is a line. If you can take 1 point and 2 points, then you can take a third point, and 3 points is a lamina, or a portion of a surface. So the difference here between working with 1, 2 and 3 points is nothing. It's just repetition of the same principles that we've just seen, and we will practice. Back to paper. So now, having seen that video, I'm going to move on now to sheets number 4, and I think I have 5 again straight after. 4 and 5 pose the exact same question. That's not a mistake. That's so that you can practice 2 different methods of solving. The first one I'm going to do, work on number 4 here, and I'm going to solve this question using a horizontal section cut. I would suggest you drop the note down there of what you're using. And the second note is a horizontal section will show a line parallel to the horizontal trace. So, really important little point right there. A horizontal section through an oblique plane, of course, will show a line parallel to the horizontal trace. So, really, really important line. Let's get going. So, let's put this into action. That is the angle of my horizontal trace right there. My horizontal section gives me a line parallel to that trace. That line right there, parallel to the trace, as we saw, where it hits the XY line, where it hits the vertical plane, as we look at plan, the XY line is the vertical plane, we need to bring it up to hit the trace. And from the point where it hits the trace, I'm going to show my horizontal cut. From the point where it hits the trace, show my horizontal cut. And a point in one view and a point in the next view have to line up. That is point P. Point P found using a horizontal section cut. Next sheet we're going to use a vertical section cut, but for now there's our horizontal section cut, showing a horizontal line right there which represents the cut. Moving on to sheet number 5. This time I'm going to use a vertical section cut. And a vertical section cut will show a line parallel to the vertical trace. So there's a little bit of theory into this one. So a vertical section cut will show a line parallel to the vertical trace. There's our little bit of theory, there's our rule this time, and a bit of understanding that we might have taken from that SolidWorks video. What does the vertical section cut look like? Well, it just simply looks like a line parallel to the vertical plane right there. I need to bring that up to my XY, which is onto my elevation. And I need to go, and I forgot to put my labels in, there's V, T, H. A vertical section cut gives us a line parallel to the vertical trace. That's what the section cut looks like right there. A line parallel to the vertical trace. A point lines up on itself in every view, so that is point P right here. As you move on to the next few sheets, you're going to have to keep in mind that, of course, it works backwards. If we have the point P in elevation, we can use our first method here. If you have the point P in elevation, you can come across to hit the trace. You can come straight down onto the XY and parallel to the horizontal trace, dropping it to find the point. Or using our vertical section cut method, you can come parallel to the vertical trace down to hit the horizontal and across and down to hit. So either way, whatever way you want to work this, you work it with that method. If a question is repeated a second time on the second page, solve it using a different method. No, that's it for now for this portion. We're going to go back on that should actually be enough to take you right through from pages, I think 5, 6 all the way up to page 12 and 13 and 14, I think. So what we've just covered right now in SOLIDWORKS and here using our two different methods take you up to page 14. I'm going to go back to SOLIDWORKS for a minute. I'm going to deal with the theory involved on page 15 and 16 when you're given a lamina and you don't actually have any traces at all. So I'm going to be skipping right ahead on paper. The next question I'm going to do is sheet number 16 right here. But before I do it on paper, I want to have a look at it on SOLIDWORKS and just see the theory behind it. Now we're nearly finished with our first video tutorial on the basics of points, lines and planes. Last example I'm going to go through on this video is going to be just over here now, following on from our horizontal and vertical sections, and once we have all the understanding of the theory here, well, we're going to move on to this one here. So right there is, we might just call it a triangle, but it's a lamina. A lamina is a portion of a surface. It is a defined area within a full surface or full surface plane. So if I just took a small section of this guy right here, well, that would be considered a lamina. What I want is this. If I have the lamina, I want to find the traces of the plane that lamina lies on. I think maybe we might start to, if we had this in SOLIDWORKS, we'd probably start off by doing something like this and trying to see, right, if I can see it there as an edge, I know that that's where the plane is. Because if we just think back to this one right here, if I put 3 points on my plane and had a triangular lamina on the plane, I can see an edge view of the plane and an edge view of the surface all at the same time. So that's what we'd be kind of thinking about here, and you'd be thinking, right, so if I wanted to do it that way, finding edge views, I could, absolutely could, but there's a nicer, kind of an easier way to get started with. The one that we're going to do right now is this. We're going to extend the edges of the lamina right down to hit the ground. And I'm going to extend the second edge of the lamina right down to hit the ground. So this is what it looks like. You take any one edge from a point and a point, and you extend through to hit the ground. Sometimes questions can be depicted in a sort of a complex way where these edges don't really work out and you can't really hit them on the ground that easily. Well, there's nothing at all wrong with doing something like this if you need to, taking it through any random point to hit the ground. So that is also an option if we get stuck. For this question, the way it's set up, we'll have no problem. So we can take any edge right down through and hit the ground. And if we do that a second time, hit the ground, well, right now we have 2 points on the ground, which means we're able to draw a line through the points. We can draw a horizontal trace. So the oblique plane that lies in here, that this lamina is part of, well, that's the horizontal trace. And if I can look along the trace and find a point view of the trace, I'll see an edge view of the whole surface right there. So that's the bit of theory we'll keep in mind. I'm going to use this method right here again. I'm going to use this one in blue, a horizontal section through a point to grab a point on the vertical trace. So if we just have a look in 3D, this is what it looks like. This is a horizontal section through that point. That line is parallel to my horizontal trace. That gives me my vertical trace. So the horizontal section through any point in the lamina, and if I did the horizontal section through this point, it would still land me perfectly on the vertical trace. So that's my next part, and the final part here is actually just dropping in the lamina. There it is, using the two traces that I found, and the outline here at the end doesn't matter, whatever shape you want, it's an unlimited size. That is that clear surface. I put it in as a clear glass, I think, material here on SolidWorks. That clear surface there contains the lamina, and we found it by extending an edge through, finding a horizontal trace, and dropping in a horizontal cut there. So quite a bit involved in this one now. Bit of thinking involved. The theory is all the same as before, just a little bit of extra thinking involved in that. So we're going to go back onto our page again for sheet number 16. So sheet number 16 here. Find the traces of the plane that contain the lamina ABC, and we've just seen the theory behind it there on SolidWorks. So let's get going. I'm going to start off by extending any one edge. So hopefully this all fits on the page, and if it doesn't, we'll come up with some other methods of doing it. So B, I'm going to take the edge from B through C and extend it down to hit the ground. And where B and C hit the ground, they hit it at point number 1 there, I'll just call it. I want to find point number 1 down in plan, so I'll just project it down to plan. And I'm going to do the same process again. So I extended from B down through C until I hit the horizontal plane. I'm going to extend from B down through C, and I do it just off the border right there, and that is point 1. Point 1 is on the ground, so I went from B down through C until I hit point 1. So point 1 is a point on the ground. If I do the same thing again, I'm going to extend from B through A, starting at B up top, going on down through A to hit the ground at point number 2 there. This is going to be really close to A now, but that's okay. I'm looking for point 2 down below, so I'll do the same process from B down through A, from B through A. Hard to even see that one now, but that's point 2. It's in there right in the middle of point A. If I have 2 points on the ground, point 1 and point 2, I can define my horizontal trace. So that's the start, that's my horizontal trace. And the easiest way to get a vertical trace, if I just change color here maybe so it stands out nice and clear, the easiest way to get a vertical trace is to just do a section cut. So I'm going to use a horizontal section cut, which gives me a line parallel to my horizontal trace. That line is parallel to the horizontal trace. It's a horizontal section cut through point B, so I know that it's going to be horizontal section cut through point B right there, horizontal line. And I just need to link them up then. That's a point in the vertical trace, just like we saw at the beginning of this video, or sorry, at an earlier stage of this video. There's my vertical trace right there. Now, that's it for the first video. I'm going to be moving on. There's one more method that I'll come back to in terms of finding the traces when you're given a lamina. There's one more method, and I'll get back to it at a later stage in this series of videos. That's the first video that takes us through sheet 1 to 16. So I hope this was helpful, and I'll be uploading another video soon that will contain some more information about the next pages to come. Thanks very much for watching.